Hello guys, this is the class 7 of the mineralogy class, and we are going to go over the X-ray topic, the X-ray crystallography. So first is the elements of X-ray crystallography. So X-ray crystallography is a technique. It's just like how we do X-ray in medical terms only. The same way in the X-ray is being done in crystallography to understand the internal structure, even the like every chemical elements present, every chemical compounds presents, how the mineral structure is from micro scale level, uh, everything crystal structure to the different phases, the crystallographic orientations, um, everything we can understand using this X-ray technique. Okay, so the X-ray crystallography is a technique used to determine the atomic and molecular structure of crystals by measuring the angles and intensities of X-rays diffracted from a crystal. Scientists can create a three-dimensional image of electron density revealing the atomic positions. So we will be able to understand the different atomic positions in the crystals. Also, we will be able to understand the defects if there are any in a crystal. So this extra crystallography is very useful for minerals in which we are not being able to identify those minerals, say in a very small grain rock, in a very fine grain rock we are not being able to identify crystals in optical, using optical techniques, okay, using microscopes. So then we will use this X-ray crystallography. This is a very advanced technique, nowadays very frequently used, to identify what type of mineral is present in the rock and what are the different elements in the rock, or the different compounds in the rock. Is there any impurities present? Is there any defects present? Everything we will be able to understand using X-rays. Okay. Now, the key elements. The key elements are X-ray source. So produces X-rays using a tube or synchrotron, typically with wavelength from zero point 0.5 to 2.5 angstrom. There will be a number of terms which are not geological, but which are actually physics related or technical terms, like goniometer. Then there is synchrotron, like the dog. This is actually instruments names. Okay, so you just have to mug up all these instruments names, because, or you can do what you can do is you can search it in Google to understand how this different instruments looks like, so that you can get an idea of how these are. Okay, so typically with wavelength of zero point 0.5 to 2.5 angstroms, this is the X-ray source which produces the X-rays. Okay, now there is goniometer. Goniometer is the positions the crystal precisely in the X-ray beam. So this is actually a stage where you position the mineral, allowing systematic rotation and tilting for the data collection. So it can move in 360 degrees. Okay, so this thing can move, have a goniometer which can move the crystal at different angles, so that the X-rays can fall at different angles and give the data based on different angles. Okay, so we need all these things. We will go through this later. Then there is director. Director is which measures the intensity and positions of diffracted X-rays using technologies like photographic films, CCDs, and hybrid pixel detectors. So we have a source, we have a stage, goniometer, then we have a detector. Then data processing. So integrates and reduces diffraction images to correct for noise and detector sensitivity, converting raw data into usable formats. So integrates, reduces the diffraction image to correct for noise. Different types of noises and different types of unrelevant things are removed using data processing. Okay, then there is the electron density map generated through Fourier transformations and phase information, revealing the distribution of electron density in the crystal. So we will not go through how exactly this thing works, because this is very advanced, how the X-ray processing takes place. Because what geologists do is that we have a machine, we give the sample, and we get ourselves a output. So this is all that matters. Okay, so what happens in inside the thing is not our job. Okay, this is the job of a, say, mechanical engineer, or say electrical engineer, electronics engineer, because all these things we not be able to process. Okay, so I'll just go through how these things actually work, what is the theorem behind it, but not how this processing takes place. Okay, so, model building and refinement constructs an initial molecular model based on electron density and refines it to match experimental data closely. And validation uses tools like R factor and correlation coefficients to ensure, these are all mathematical terms, okay, to ensure accuracy and reliability of the final molecular structure. Okay, so what we have is we have a source from which X-ray is created, which hits on our sample, which is holded by a goniometer or a stage. Then it is projected into a detector, which detects the different variables that we use to understand how and what the mineral are present in the rock. All the things that we need, we will be able to understand using those parameters that we get from the receiver or from the detector or from the output. Okay. Okay, so now we'll go through the methods are, there are two methods. First is the X-ray powder diffraction powder method. X-ray powder method, the principle involved is X-ray diffraction, or you can say this is called XRD means X-ray diffraction or XRD. Now you will understand Bragg's law. If we know the wavelength lambda of X-ray and measure the angle theta, we can determine the d spacing of the crystal planes with the equation 2d sine theta equals to n lambda. Okay. Now I'll bring the whiteboard, and I'll just explain you some few concepts before going ahead. Okay. This may take some time, but I think by doing this you will be understand how this X-ray things work. Okay. So let me begin. So you know these X-rays have a certain wavelength. So I'll teach you how this X-ray works and how what theorem this X-ray will be working. Say this is a wave. So we will have lambda of certain wavelength. Okay, so this is a lambda of certain wavelength. Okay. Now say we have a crystal like this. We have a crystal like this of, these are the atoms present in the crystal, having some certain distance in between them, which is fixed. You know, we have learned crystallography. So these distances are actually fixed. Okay. For certain different for different crystals. Okay. Now this is, we can define it as lambda also. Okay. Now say this is an X-ray coming, and this will be diffracted. Okay, this will be diffracted. This is called diffraction. So this is used, diffraction, this is used to understand the distance between the atoms. So this diffraction is directly proportional to what the distance between the atom is. Okay, this is just a simple overview of how this X-ray works. Okay, now in the next page I'll draw how this, you know, what is interference. Now interference, what is interference? Interference is just how X-rays are interacting with each other. Okay, how X-rays are interacting with each other. Now you all know, I think, that when one ray superimposes another ray, then it will be constructive interference, and the amplitude will be much higher, right? Amplitude will be much higher. Similarly, when there is a shift in the two X-rays, this will have a destructive interference. So amplitude will be lower or diminished amplitudes. This is the amplitude. Okay, diminished amplitude for destructive interference and enhanced amplitude for constructive interference. So this will happen in X-rays. Okay, how we will talk about that. So let's say this is an atom. This is the nucleus of the atom, and these are the electrons. Okay. Now what happens is when X-rays hits this electron, some of the energies get absorbed. Okay. So when X-rays encounters these atoms, some energies gets absorbed, some get absorbed, whereas some gets dissipated. Some gets absorbed, whereas some gets dissipated. Okay. So if the energy is not enough to the kick an electron, then the energy has to be dissipated or released. So that form is actually, so when this is dissipated in the form of an X-ray. A new X-ray will be formed. So when it hits an electron, some energy gets absorbed inside it, some energy gets absorbed inside it, whereas some get dissipated in a new X-ray, right? That is called as elastic scattering. Elastic scattering. Okay, elastic scattering. I'm trying to explain it to you so that to those students who doesn't have a science background but want to study geology optional for IFoS, but not being able to understand how this thing is actually works. So I'm just trying to explain it to you in a layman language. Okay, so this is called elastic scattering. Now we all know that these atoms have particular spacing. Different atoms of sorry, atoms of different crystals or different minerals will have different spacing which is unique to them. Okay, which is unique to them, and on the basis of this d spacing, called as d spacing, we can identify which mineral it is using X-ray diffraction methods. Okay, so this is the key thing that we try to identify. What is the d spacing? So atoms have well defined distances in crystals called as d spacing. This is say a face of an atom, say 0, 0, 1, and this is the atoms in it, and this is the d spacing in it. Okay, now when this X-ray passes through it, it results in diffraction. I've told you when this X-ray passes through it, it will have diffraction. Diffraction, right? This is the incident ray, this is the refracted ray. Now strong amplification or constructive interference occurs at very specific angle. So this happens at a very specific angle. Okay, this happens at a very specific angle. This results in strong amplification. Strong amplification, or you can say constructive interference, right? We have just discussed in the previous page. Occurs at a very specific angle, results in constructive interference, right? Now how this will look like? This will look like this. Say I draw again those atoms in a crystal, and then let's say this one travels here, then goes here. This is the incident ray, this is the diffracted ray with strong, amplitude, and this is the 2 theta angle. 2 theta angle at specific angles, this diffracts. 2 theta angle. Okay, or if I'm trying to say, let's say draw this, so that I can derive the theorem of Bragg's law. It's a tough diagram to draw, but still I'll try. So like this is diffracted. Okay, this will also be diffracted. Say this is lambda by 2, this is lambda by 2. Diffraction will be lambda by 2, lambda by 2. Here it will be lambda by lambda. See, this is increasing, right? This thing will keep on increasing. This will be whole number of lambda, lambda by 2, lambda by 2, then lambda, lambda, then 2 lambda, 2 lambda, then like that. These waves must be in alignment. Okay, these waves must be in alignment, and that is it should travel in whole numbers of wavelengths. This should travel in whole numbers of wavelength. Okay, so first will be lambda by 2, lambda by 2, then lambda by lambda, like that. Okay, so here the incident side is lambda by 2, whereas the diffracted side is also lambda by 2. Here the incident side is lambda. See, it has increased, and the diffracted side is also lambda. Okay, like that. So we can just take, say, this one, okay, this triangle, and try to derive the Bragg's law. So how will I do it? I will do it like this. Say this is triangle, this is a the despacing distance, this is theta. Remember, this is 2 theta. Okay, it's refined as 2 theta, whereas this is taken as theta because this is half the angle, right? Half the angle, theta, and this will be lambda by 2. Okay, this will be lambda by 2. Now we will try to derive it. Okay, how will derive it? So we can see that just by simple trigonometry, we have sine theta equals to lambda by 2d, right? Lambda by 2d. Then we have lambda equals to 2d sine theta, right? Okay, so now for n number of times, we have n lambda equals to 2d sine theta. This is the Bragg's law. Got it? I'll just draw again it to you so that it remains side by side. Just by simple, just by simple trigonometry, you will be able to derive this equation, right? So this is Bragg's law. I hope you understand how this equation comes. Okay. Okay. Now coming to the topic, Bragg's law. We have explained what Bragg's law is. Since you can see here the incident light coming here and then outgoing, right? So X-ray can interact and reflect off the atomic planes in a crystal structure. Ray A reflects from the upper atomic plane. Ray B reflects from the lower atomic plane at the same angle, theta. Here you can see theta, 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 theta. Okay. So you can say d sine theta, d sine theta. This is d. Okay. This is the plane HKL. Incident light going, incident line hitting, and then going up. And the ray B travels an exact extra distance of 2d sine theta. This extra distance it is covering. See this one. So constructive interference occurs when 2d sine theta goes to n lambda. Okay. This is the Bragg's law. So what is the procedure? Here you can see this is the X-ray tube or the source It is hitting on the goniometer stage. That is sample powder. Here we keep the sample here. It hits, then it goes into detector where it is processed, and then it gives us the output to the computer. Using that, we are able to understand the all the things that we need. Okay. So the sample preparation, minerals are grounded into fine powder with random crystal orientation for X-ray diffraction. Okay. So it is first powdered and then with random crystal orientation, because we are powdering it, so the crystal orientation will be damaged, right? For extra diffraction, we need to powder it. For monochromatic light is used X-ray powder diffractometer, where the monochromatic light, monochromatic X-rays, that is monochromatic means just say black and white light is used from a rotating tube to scan angles 0 to 90 degrees. So 0 to 90 degrees are where the scanning happens at different angles. The angles are changed constantly using a goniometer stage with diffracted rays detected by a rotating electronic detector. So all things rotate. Okay, this X-ray tube rotates, this goniometer is also rotating, and the detector is also rotating. Everything can rotate and then gives different angles so that we can scan the each particle of minerals and then give us a proper output. Again, the goniometer, the angle theta is tracked by an instrument that rotates both the X-ray tube and detector with data set sent to computer for analysis. Okay. The data analysis, X-ray intensity versus 2 theta angle is plotted. Here you can see the intensities of X-ray that is given by the output by our detector is as given as spikes at different 2 theta angle. So these spikes given at different 2 theta angle is plotted as a graph. So X-ray intensity means the spikes versus the 2 theta angle is plotted to identify diffraction peaks. These are actually diffraction peaks. And D-spacing is calculated using Bragg's law for each peak. Okay. So this peak have some value, the intensity have some value. With the help of that, at certain 2 theta, that this value is happening, that means this has this type of a mineral or this type of element present. Okay. Now how do we identify what type of number denotes what type of mineral? So we use this, we have a standard book called ICDT, that is a standard reference database. I'll write it to you. we have a we have a ICDT standard reference database. With the help of that, we are able to identify at what 2 theta what peaks are being shown. Okay. Intensity, right? So using this ICDD reference, which comes with the machine only, if you buy a machine or XRD, you'll automatically get this ICDD, or it can be present as a soft copy. So using that, we just get the how the different minerals are present. What type of different minerals are present, we will be able to understand. So XRD provides detailed structural and chemical information revealing the atomic structure of materials. Okay. And mineral index also there. One can then work out the crystal structure and associate each of the diffraction peaks with a different atomic plane in terms of mineral index of the plane HKL. So we also get how the HKL things are there, how we will be able to understand the forms also. All the things that we have read in crystallography, we will be able to understand all those things using XRD. Okay. Okay. Now we have the second topic, that is the XRF. XRF is a different process. XRD we have learned. Now we will go XRF. XRF means X-ray fluorescence spectroscopy. Is a technique used to analyze the elemental composition of the material. Remember, in XRD we get to have the different minerals present in the rock, say olivine, garnet, all those things. But in XRF, we will be able to understand the elemental composition of a mineral. Say we have like SiO2, if it is there, if it has Fe2O3, if it has Fe3O4, if it has say MgO, okay, like that. So compounds and elements we will be able to understand using XRF, not the mineral assemblage. Okay. So the X-ray technique is used to analyze the elemental composition of the material. It works based on the principle of X-ray emission from atoms when they are excited by high energy X-rays. So what is the procedure? Procedure is the sample preparation. The material, often in the form of powder or pressed pellet, is exposed to high energy X-rays emitted from an X-ray tube. So if we want, we can do it both ways. Like X-ray fluorescence is also sometimes called a non-destructive method, because in X-ray fluorescence we can either give a powdered sample, okay, or a pressed pellet, or even we can give a chip. Okay, so what we can do is, let's say, we can either give a pressed pellet. A pressed pellet is like, say this is a rock sample, we then powder it. Okay, we then powder it into, like, this is a powder. Then we put this thing in a pressed pellet. This is a pellet. We put inside the powder here and then we press it. Okay, then press it. It's just like a coin. Okay, this is called a pressed pellet. This is one way of putting a sample. Or XRF is also called non-destructive method. See here, if you are powdering the sample, we are destroying the in situ condition of the different minerals, right? But in non-destructive method, say this is a mineral, we take a chip from it. Take a chip from it. Chip is like just like a sheet, small sheet of mineral. Okay, then we mount it over our stage. We mount it over a stage, and then at different angles it detects, and then detector, source, this also moves, this also moves, this also moves. Okay, everything is moving at different angles. It will detect, and then we will get a non-destructive analysis of the sample. So we will be able to identify how, uh, like, there will be no alteration in the mineral. Okay, so both ways we can do it, using pressed pellets or using chips. Here it is written as pressed pellet. It's exposed to high energy X-ray emitted from the X-ray tube. The X-ray excitation, the incoming X-rays dislodge inertial electrons from atoms in the sample. The process generate characteristics X-rays. See, this will, when incoming X-ray, that is from the source, dislodges the inertial electrons from the atoms, this process generates characteristics X-rays called fluorescence, as the electrons from high energy levels fill the vacancies in the lowest in inertial. The electrons from the high energy goes to the inertial and then fills the vacancy. Detection. A detector measures the intensity energy of these characteristics X-rays. Right. So detection is simple. Then there is analysis. The resulting spectrum shows peaks corresponding to the elemental composition of the sample. Quantification is achieved by comparing peak intensities to known standards. The same thing happens with just like in XRD. These things comes, but here the only difference is it will give us the compound or elemental analysis, whereas in the above it will give us the mineral assemblage present in the rock. So advantages are, this non-destructive. This technique does not damage the sample, allowing for repeat analysis if you are using a chip sample. Speed and sensitivity provides rapid analysis with high sensitivity for a wide range of elements, and detailed elemental information offers insights into both major and trace element present in the sample. So this is a very good way of analyzing or chemical analysis of your rock or mineral, XRD and XRF both. I have done some XRF and XRD study during my thesis in my college. and this is a very good, I can say this is a very good technique. So this is it. uh, but okay, so just let me give you some some tips for the exam, or some extra like material for the exam. Say, if they have asked like what is the difference between, why should we do it, if you are getting like if you are studying it in optical mineralogy or in the microscope, we will be able to understand the mineral assemblage. So why we have the hassle of doing XRD. So in XRD we will get to understand, in XRF also we'll get to understand the different polymorphs. So different polymorphs can be understood using, I think I have told you what polymorphs are, right, in the previous classes. So different polymorphs we will be able to understand using XRD and XRF. Then soil analysis can be done using XRD and XRF. Weathering products like goethite, hematite, all these things that are not observed in optical mineralogy because they are very fine grained and very messy in structure. So those things like soil analysis, matrix analysis, cement analysis, or we say goethite, hematite, these are all actually weathered products. Okay, these are very much used in remote sensing as well as in engineering geology. Okay, so then transformation minerals, like how metamorphism is taking place, what the different type of elemental analysis is, elements are changing. Okay, then we can find out the difference between calcite and aragonite, which is very hard to identify using optical mineralogy. Okay, so this was it for the X-ray part. Then we will move on to silicates now.